to a little advanced topics. Since some of you have not learned statistics, and this one you might want to skip if you have no clue. I said linear regression have the second purpose is doing hypothesis testing of your scientific assumption. So in a lot of research, you make your assumption based on the data you wanted to see if your assumption is reasonable, or in other words, scientific, you say you don't have strong evidence or say adequate evidence to deny your assumption. That's when your assumption makes sense. Or you say based on statistics, the assumption is not right. That basically roughly speaking, if anything, in this 95% of confident interval, or any interval you want to set, you say you don't have enough evidence to deny your hypothesis. Basically, you agree, but you don't say that way. You say you don't have enough evidence to deny. But if anything out of this range, we call it the outlier. The outlier. If it's outlier, you say, okay, the statistical evidence shows the assumption is not true. This is, again, another application of the least square analysis, and also be another application of Lagrange's method. Let's look at an example. In the example, I can make a little hypothesis. For example, in the previous example, I can say, hey, it looks like a promotion and the advertising, they give me the same result based on the deviation. There's no significant difference. I should put in two different variables. Can I merge the two variables and put all the money together as one variable? Well, that's your assumption. And in the example, your assumption basically say the beta 2 equals the beta 3. Or say beta 1 equal beta 2, I think. We have the beta 0. And that's your assumption. Or you can say, well, I look at this model, the opponent's cell have nothing to do with our cell. We can just drop the last variable, beta 3, just don't consider it. And now the question is, if either you make this constraint or drop the third variable, are you going to get the same deviation in the model and the average? Well, when I say the same, it's quarter and a quarter. You will not get exactly the same mathematically, but you will get the same statistically. They are going to be in the same confidence interval, and then you can make this assumption if you want. So in this idea, what assumption you make, you write into a matrix equation, which simply write this. Actually, C is a matrix, and the beta is a n by 1 vector, and the C is n by m matrix. So equal to theta could be just the 0 vector, anything you want. So besides the original problem, you try to minimize this least square, the residue, and you add another constraint. That's your hypothesis. Well, you can carry on the same statistic analysis. We are not going to go through this based on the time, but let me remind you the tool. The Lagrange multiply method is pretty simple. All you need to say is the gradient of the least square, the objective function, is proportional to the gradient of the constraint. That's the Lagrange's method. When we write it this way, remember, you, in the real situation, have m equations because you have m independent, actually m plus 1. M plus 1 equations. And based on those equations, we can solve the system. Let's see. We are not going to go through this, but if you want, I can show you how to do it line by line. It's easier for you to start right into a real matrix. Let's make it n equal 4, m equal 3 to see what happened. And then you're going to figure it out. So we take this derivative and equal that one. In the end, this help you to solve this lambda. And then, based on the lambda you solve, let me see. And then you're going to solve this beta as the estimate. You know, statistical, when it's an estimate, we put a hat on the beta. That's not the real one. You do not know the real one. And this little c means under the constraint, under your assumption. And the final result, based on the calculation we have, is the original beta hat. That's the solution without the constraint. Without the constraint, and then you add this matrix. Well, from the original equation, we can solve this matrix and put it all together. Looks pretty complicated, but in the end, it's not too bad. And in the second equation, we solve the beta. This is the original one. This is the real difference. And look at the structure. This is the data of the independent variable. That's a square matrix, inverse it. And the last term is really matter. That's the constraint. And then your final result is really the original observation at this component. And it really depends on the constraint, make sense or not. You're going to see the difference. So what is the difference you're going to compare? Well, let's look at the example again. In the relationship between the advertising promotion to the sale, if I make the assumption the advertising and the promotion have no difference, then you get an equation here as a constraint. See, that's beta 1 equal beta 2. If we multiply, that's nothing. Beta 1 minus beta 2 equals 0. And then your theta is 0 in this case. And with that, add to your original system, we can look at the new regression model. The new regression model is going to be a little more complicated, but use MATLAB. Your C is this matrix. That's a column, a row. And the A is the x prime times x, the same x as the table given to you. Get the inverse. And the lambda is the equation we given a moment ago. Let me show you the lambda. That's the lambda's right here. And you got everything. All you need is check, do I have those data? Yes, you do. And you put it into the place. See, you got the lambda. That's the Lagrange's multiply. And then this BC is the beta C in the formula based on the original B. That's my original beta for the previous example. And add all those things. And then what you get is the linear regression. So in that regression model, of course, you need to call to the regression. And what we get is this model. Well, again, you get the 4 parameters. Obviously, as you are constrained, the beta 1, which is the advertising, and the beta 2, the promotion, they are the same. That's why your assumption, of course, you get this linear regression. So compared to the previous one, let me see where's our previous one. Not yet. Okay, here you go. This is the previous one. That's 48, 49, and now become 50. And this is 59, now become 50. And this is 65, become 70. Well, of course, mathematically, that's different. But statistically, are they really different? Then we need to look at the test of the hypothesis. There's all different statistical methods. Here we only look at one. What do we look? It's the deviation. Without the constraint and the deviation and the constraint. And that's the formula. And your n, actually is n minus 1, should be 14. N is 15. Well, then we compare. One thing should be obvious. Under the constraint, your model is not going to be as good as without any constraint. Intuitively, the more parameter you think, the more accurate your model become, and then the less deviation you should have. So that must be true. The constraint of the deviation under the constraint is bigger than the deviation you originally had. All we need is look at the ratio. If this ratio is close to 1, then we have no confidence or less confidence to decline our hypothesis. But if the ratio here is way too big, we probably think, well, this new model really very different from the old model. I'm not going to take that. I still need to consider them as 2 different variables. That's how we do hypothesis test. And of course, you need a little more statistic to understand all the detail. In this example, we found, if I combine the 2 terms, I found this difference is almost nothing. It's almost 1, neglectable. In that sense, we can say, yeah, you really don't need to consider the advertising, the promotion as 2 separate variables. To make it easier, you combine the 2, and you can make an easy model. And that's what we get. All right, this is for today, and see you next time. Thank you for your participation.